Uh-oh, center of mass. Center of mass is easy for things like spheres. Center of mass in the center. Some things are more complicated though. For instance, a box and another box. Where do you think the center of mass is? If I draw a coordinate system, we could draw a coordinate system like right here, for instance. Do you think the center of mass is right here at the origin? I don't think so. There seems to be more mass over on the left side, so we're going to have to say the center of mass is somewhere over here, or maybe over here. There's another cool system where the center of mass is something interesting. Here's the Earth, and here's the Moon. Well, it's probably like way over here. There's the Moon right there. The center of mass between the Earth and the Moon is actually just within the Earth. Whoa. And we'll call that the position of the center of mass. It's the x position of the center of mass of the system. This might be the x position of the center of mass of the system. How do we find it? Well, we add up all the mass and we divide by the total mass. But we're not just adding up all the mass, we're adding up the mass at its position. So let's try to make this a little bit more concrete. Let's say that this is 8 kilograms and this is 1 kilogram, and this is located at -4 meters, and this is located at +4 meters. And we can get ourselves an actual position of the center of mass using this equation. Here's the position of the center of mass, and it says, well, it's going to be the position of mass 1 times the mass of mass 1 plus the position of mass 2 times the mass of mass 2 divided by the total mass. Okay, let's see how this works. This is a simple example of the equation for just two objects. Let's plug in some numbers. x1 finds itself at -4 meters. We take that and we multiply it by 8 kilograms. One way of looking at this is that we're weighting this box heavier because it actually has more mass. It is more significant in the equation. That's what I mean by saying weighting in this context. And then I want to add on the position of mass 2, which is at +4 meters, and multiply that by the mass of m2, which is 1 kilogram. Notice it has a weaker weighting in the equation. It is less significant because it has significantly less mass. And then we're going to divide this by the total mass, which in our case is 9 kilograms. And we get, ooh man, this is -32 and this is 4. What's -32 plus 4, Wayne?
Oh, -32 plus 4?
Yeah, go.
Oh, 28.
Very good. But negative,
Positive.
right? -28
yeah.
kilogram meters. Kilogram meters, that's that weird unit right there. And then I'm supposed to divide that by 9 kilograms. And I'm going to pretend that's about 27 because I can't divide that easily in my head. No, sure I can, it's fine. So we're going to get -3 and 1/9. 3.11111. I can really divide really well, right, Wayne? Isn't that impressive? So this, look at the units right here. This got kilogram meters and kilograms down in the denominator. So the kilograms are canceling out, and we get meters left over. This is the position. Oh, sorry, you can't see it because I have too many ones there. This is the position of the center of mass. It says that the position is not quite at -4, but the position is right here at -3 and 1/9. That's where the center of mass is for this simple system. So we need to go to another equation. This new equation will be a little bit more general. It will consider the possibility that we've got lots of masses scattered around here. And that will be, position of the center of mass is, well, we're going to have to add up all the masses. So we're going to have to start at I equals 1 and go to the total number of masses. And we're going to note the position of each mass and multiply it by how much mass is at each location. And then we'll divide that by, no, let's do it like this. We don't want to do it inside that sum. I'm going to find this sum. That's what I did here. I found the sum first, and then I divided it by the total amount of mass. So I'm going to say I equals 1 to n of all the masses. This tells me where in x the center of mass is located. However, I might have masses that are scattered around in y also. So I guess we need to be a little bit more careful. I need to tell you where in y it's located. Here's the y position of the center of mass, and I'm going to leave it as an exercise for you to find the z position of the center of mass. Good luck. Check this out. I'm going to take I going from 1 to n, this is summation, says I've got to do all of these little multiplication problems and add them all up together until I find the total mass. So it's going to be the y position of mass I times the mass of mass I, and then I have to divide that by the total mass, which is I 1 to n m I. This right here, let me circle this and call this to your attention. This is simply the total mass of the system. That's a way for us to find the total mass of the system. So the z, how different would that be? Wayne, you see this pattern here? There's the x for x, there's the y for y, z, no problem, right?
Yeah.
No problem at all. Okay, so center of mass is interesting for certain objects. It's not interesting for spheres. It's relatively interesting for bananas. You can find the center of mass of the banana by moving your fingers closer and closer together. The balance point will indicate the center of mass. Okay, and the balance point of the hammer, surprising, right? And fun, check it out. Balance point of the hammer, way over there by that side. Good. Another way to practically find the center of mass of an object is to dangle it from a point. The center of mass must be directly beneath my finger because the object doesn't feel any torque right now. So it's directly beneath on a line right there. But you don't know where on that line, right? So you dangle it from another point. Oh, it's right in the middle of the banana, kind of right there-ish. That's reasonable. Here's an object that doesn't have a center of mass within itself. What do you think the center of mass is for that? There-ish? Probably is. Check this out. We can dangle it, and we find the center of mass is somewhere below this line. So somewhere in here, and we can dangle it again, and we find the center of mass is somewhere on this line. So where those two lines intersect, that is the center of mass for the object. We can also do the zooming in with the fingers. The normal force adjusts to make the friction cause my hands to move as long as I'm level to find the center of mass. So the center of mass is directly below this point also. It looks like the center of mass is probably right there for this object, outside of the object itself, but fun.
Good.
Good. So the final thing that I want to say about the center of mass is, strictly speaking, you don't want to add up all these masses. You want to be able to do, ooh, look at this as a sum. It reminds me of a Riemann sum. You want to be able to do integrals. Baby, look at this. This is really what the x position of the center of mass is. Really, the x position of the center of mass is going to be the integral over the entire thing. I'll say the integral over the volume of the object. Integrate over the volume, and I'm going to say that we integrate, well, we're going to integrate the mass over all positions in the x direction. And then I have to divide it by the entire mass. And the way to do that is to integrate over the volume, the mass, dm, like that. So this says how we can actually do it using the calculus language. We need the integral of m over x divided by the integral of m. This is all the mass. This is where the heck the mass is, multiplied by how much mass is there. If there's no mass at a certain point, we don't need to take the integral because that portion of the integral will be 0. We can also find other averages of this. Notice that the position of the center of mass has units of position because this is position times mass, and it's divided by mass, so it has units of position. We could find the velocity of the center of mass. The velocity of the center of mass, well, you want to use the calculus language? The velocity of the center of mass would say integrate over the whole thing, integrate over the volume, the velocity of the mass times where it is, and divide by, we should divide by the total mass, the integral over the mass. I'm going to change this just a little bit. I'm going to make it the integral of the position over the mass. So these have a very similar flavor to them. Yeah, there we go. I like that a lot better. Okay, so this says integrate the position over any mass. If you don't have mass, then you don't add that position in, like we saw before. You could also find the acceleration of the center of mass. And the cool thing is, when things are in equilibrium, they can spin around their center of mass. So for instance, this guy right here, whoops, that shows you the position of the center of mass of the hammer because it will circle around its center of mass, and that's all that it can do. Yeah, that's it on center of mass. That's all I have to say. Oh, I guess I should say that, man, maybe I should derive it. No, I can't do it. I'm gonna give you one sentence. The center of mass of a system accelerates exactly as if it were a point particle. If all the mass in the system were concentrated at the center of mass. So this gives us all kinds of power. Like for this thing right here, we could say that this is really just two objects. This is an object here whose center of mass is in the middle because it's uniform, and an object here whose center of mass is in the middle. And guess what? The location of the center of mass for the whole thing is the average of this position and that position. So that's why it appears right here. It's halfway between here and here. It's got to be right there because that's the average of the average positions of all the masses. Good, so you can make a lot of shortcuts. Let me know if you have some questions. There's another cool system where the center of mass is something interesting. Here's the Earth, and here's the Moon. Well, it's probably like way over here. There's the Moon right there. The center of mass between the Earth... Whoa! Center of mass! Center of mass is easy for things like spheres. Center of mass? In the center. Some things are more complicated though. For instance, a box and another box. Where do you think the center of mass is? If I draw a coordinate system, we could draw a coordinate system like right here, for instance. Do you think the center of mass is right here at the origin? I don't think so. There seems to be more mass over on the left side, so we're going to have to say the center of mass is somewhere over here, or maybe over here. And the Moon is actually just within the Earth. Whoa. And we'll call that the position of the center of mass. It's the x position of the center of mass of the system. This